Hello students, in this video we'll discuss linear fractional transformations and the cross ratio. Let's recall, of course, we're in the setup of a linear fractional transformation. We have an LFT, LFTs, have the form T of z is AZ plus B over CZ plus D. Those are our LFTs. What I'm going to do now is I'm going to fix 3 points in the Riemann sphere. Let's fix 3 points. And you're going to see why I'm going to choose this in a second. 3 points, Z2, Z3, and Z4 in the Riemann sphere. So they can be infinity, right? So in other words, they can be complex numbers. Z2, Z3, and Z4 can be complex numbers, or they can be infinity, right? I want these points to be distinct points. I don't want them to be the same, okay? But infinity is all right. And then define an LFT, S of Z, which is going to be what? Which is going to be Z minus Z3 over Z minus Z4 over, you can sort of see how this cross ratio is coming in, over Z2 minus Z3, Z2 minus Z3 over Z2 minus Z4, okay? And so technically this S of Z is indexed by Z2, Z3, and Z4. So we're using shorthand notation. There's really S, Z2, Z3, Z4 of Z, but I don't want to be that sloppy with it. I'm just going to leave it as S of Z with this implicit notation built into the video. Okay, excellent. And so now notice, here's an elementary fact about this LFT. It's an LFT, right? It's a ratio, it's two affine functions, right, over each other. And so what's S, for example? So note, and remember, it's a bijection too, right? So this is bijection of the Riemann sphere doing. So note that S is a bijection between C hat and C hat. Great. That's follows some basic properties of LFTs. And now what? Now and S of what? Let's do S of Z2. Now you might say, wait a minute. What happens if what? What happens in a special case? What happens if Z2 is infinity, right? So if Z2 is infinity, this expression over here turns into a 1 and that becomes S. No problem, right? Now what happens if Z3 is infinity, right? So if Z3 is infinity, we're going to look at the ratio of this over this, right? So in other words, we'll flip this over into the denominator and get what? So then we'll have a, you basically use L'Hopital's rule a couple times and you'll get it for free, right? So if Z3 was infinity, then what would happen over here? So then I would put that in the denominator, and then we would pass the limits and we would get something that involved that ratio. So you can figure out what the S will be in the cases when those are infinity. Just use L'Hopital's rule and figure it out, right? Okay, so what's S of Z2 going to be? So if I plug in Z2, I will get what? Well, that's going to be a Z2 over the same thing. So S of Z2 is going to be 1. What's S of Z3? If you plug in Z3 to this, the top is going to be 0. So that's going to be 0. And S of what? And S of Z, let's find what's S of Z4 going to be. If you plug in Z4, you're in trouble. You're going to hit infinity, right? But that's fine for the Riemann sphere. Infinity is a perfectly valid point for the Riemann sphere. So in other words, I'm mapping Z2, Z3, and Z4 to 1, 0, infinity. That's a very powerful mechanism in the idea of conformal mappings. And if you're taking a graduate course in complex analysis and you're taking a qualifying exam in complex analysis, you're going to see at least one of these questions on every practice qualifying exam, almost surely, right? So not necessarily 100%, but almost surely, high likelihood you're going to see something like that. Great. So that's a very important formula to memorize, right? And so now, what's the idea? So I'm going to find the cross ratio now. Define S of Z1, Z1, Z2, Z3, Z4. It's the image under S of the point Z1 in the Riemann sphere, not necessarily one of those 3 points, right? For Z1, not Z2, Z3, Z4. And this is called the cross ratio. Cross ratio of those points of Z1, Z2, Z3, and Z4. And we've already proven something about this sort of in disguise, right? The cross ratio is real if and only if the points Z1, Z2, Z4 are concyclic. So we've already proven this. I'll send you the link to that proposition. Z1, Z2, Z3, Z4 are concyclic if and only if what? If the ratio, this cross ratio, is real. Okay, that's an easy argument, right? The opposite angles up to sum to pi, right? And that, of course, is going to force you onto the imaginary axis, right? Good. Okay. Alrighty. So that's a basic proposition of the cross ratio. We're going to come back to this in a second because it's going to help us prove it, or give it alternate proof for LFTs. Okay, so now what do I want to show? I want to show this cross ratio is invariant under LFTs, right? So there's another proposition for any LFT T, we have that T preserves cross ratios. The cross ratio of Z1, Z2, Z3, Z4 is equal to T Z1, T Z2, T Z3, and T Z4. Okay? And this follows from the fact that LFTs can have at most 2 fixed points, right? So here's a lemma before we do this proposition. Lemma LFTs. We'll do a whole video on LFT fixed points because you can classify LFTs via their fixed points. So LFTs have at most 2 fixed points. The proof of this lemma is trivial, right? Because proof, so Z is a fixed point if and only if Z times CZ plus D is equal to AZ plus B, and that's a quadratic equation, right? Quadratic equations have 2 roots at most, right? They can have a repeated root, right? But there's at most 2 fixed points, right? So it's just follows from this quadratic equation. Okay, good. And so now what I'm going to do is the following. So now let me consider, so here's the proof of the proposition, So I'm going to let, I need another letter, R as T. So let's let R be S. So in other words, I'm looking at Z2, Z3, and Z4. They're going to generate for me a what? They're going to generate for me an S. So that's the same S as generated by those things, composed with T inverse. Now, R is also a what? R is also a linear fractional transformation because it's the composition of 2 linear fractional transformations. So this R is an LFT. And now notice that what's R of what? R of T of Z1. R T of Z1 is going to be what? Is going to be S of Z1. Oh, so I want a 2 here, actually, 2. So what's R T of Z2? R T of Z2, well, the T and the T inverse can cancel out. It's going to be S of Z2, right? And S of Z2 is going to be what? S of Z2 is going to be, S of Z2 is going to be 1. And then what? R of TZ3 is going to be 0. And then R of T, what? R of T Z4 is going to be infinity. Okay? So in other words, this R happens to have the same happens to map the same points as S, right? In other words, I have these linear fractional transformations agree at 3 points, meaning they have to be the same, right? So in other words, R of, for example, Z1 is going to be what? Not Z1, but I want to do something different. Let me think carefully here. I want to make sure I don't make any mistakes. So now what do I want to do? So now I know that S of Z1 is equal to what? S of Z1 is equal to Z1, Z2, Z3, Z4. Good. Now what is R of, and so S of Z would be, if I just take this 1 out of the way, S of Z is going to be equal to this, right? Okay, but now let me plug in what? And I know that R is going to be what? R is going to be the same 3 things over here, but with the T's, right? So R of Z is going to be what? R of Z is going to be just a Z and then a T Z2, T Z3, t z4, like so. And now if I plug in t of z1 into this formula, that'll be the same as s of t1, right? So in other words, that shows me is now plug in to both these things over here. If I plug in t1 over here, that will give me this expression over here, and that will give me what? That will mean the same thing. So if I plug in, for example, t1, so it says that s implies that s of t1, so r, so carefully. It's a little bit of, it should be clear from this formula, right? So from this formula, it implies what? It implies that if I plug into r, if I plug in z of t1, then s of what? So r of t1 of z is the same as s of t1 of z. So on one hand, s of t1 of z is going to be what? S of t1 of z is going to be given by this formula over here. It's going to be t z1, t z2, t z3, and t z4. That's on one hand what it's going to be equal to, right? Just by plugging it in to this formula over here for the r formula. But it also has to be what? It also has to be s of the zt1, right? So in other words, if I put a 1 here, I should get exactly the same formula because the t and the t inverse are going to cancel out. So this formula over here has to be equal to this formula here. So any linear fractional transformation, by virtue of the fact that you can only have 2 fixed points, that's going to force this position over here. That's going to force the position that your r composed with t is going to be r composed with t clearly equal to s, right? And now, of course, that allows me to conclude that the cross ratio is preserved by any linear fractional transformation, which is going to be a very useful mechanism when improving geometric properties of LFTs. Thank you very much.